Hello and welcome to Lesson 3.4, Simple Rational Functions. Today we're going to look at all the various different things that we've seen in advanced functions to determine parts of rational functions, but we're also going to use some skills that we've learnt now with derivatives. So the first thing is, given this function f of x equals 1 over x squared minus 4, we're going to find our vertical asymptotes. And we'll find out our horizontal asymptote. Okay, so if you remember, to find the vertical asymptote, that's only when the denominator equals 0. Because if a denominator in a fraction equals 0, it's undefined. So we solve for the value of x here, and I get values of x plus or minus 2. Now, our horizontal asymptote, defined in advanced functions, is slightly different. The proper way to actually define it is the limit as x approaches plus or minus infinity of the function f of x. So we're going to calculate this limit. So what you do is you grab a calculator, you choose very large values, being positive or negative. See if they're both the same value, different values, vice versa. So I choose a very large number, I substitute it into x, and I get a value of 0. Now you might also notice that the numerator is listed as 0x squared plus 0. If you'll take the 0x squared divided by the 1x squared, because those are the more common, or sorry, more dominant values based on whatever value you choose as x gets really, really large, you'll see that it gets very close to 0. So your horizontal asymptote is y equals 0. So what we're going to do now is we're going to look at the limits as they approach these vertical and horizontal asymptotes. So first of all, we'll look at the limit specifically as x approaches positive infinity for that function first. So you choose a value very close to infinity. You grab your calculator, you plug it in, let's say 1,000 or 10,000, whatever it might be, and you substitute in. So that's what I'm going to do. And I get a value close to 0, but you'll notice that it is positive. So it's slightly above 0. We'll do the same thing as limit as x approaches negative infinity. Again, you find out that it gets close to 0, but again from above. So you don't put a plus sign on there. You use the term above to represent that it's approaching it from a positive value or from above the 0 value. Likewise, we're going to find the limits of x as we approach the value of negative 2 from the left for our function, and approaching negative 2 from the right for our function. Okay, so if we're choosing negative 2 from the left, that means we're looking at values of like negative 2.001. We substitute it in, and you'll see that you get really large numbers that are positive. So this one's approaching positive infinity. Do the same thing again, but you choose values very close to negative 2 from the right. So close to negative 1.999, let's say. Put that in, and you're going to get a value that's very close to negative infinity. In this case, it turned out to be negative 250. So getting closer to negative infinity. We'll do the same thing for the other limits. So the limit as x approaches 2 from the left, and from the right. case, if I choose, let's say, 1.999, put it in, I get a value of positive infinity. And if I choose value close to 2.001, oh, my apologies. Type that in wrong. Let me try that again. 1.99, that gives me negative infinity. This one gives me positive infinity. So this tells us some more information about the graph as they approach these asymptotes. So, based on this information, we can actually draw a sketch of what this might be. So, I'm going to say this is where 2 is. I'm going to say this is where negative 2 is. I'm going to draw my vertical asymptotes right here. I usually use dotted lines for vertical asymptotes, and horizontal asymptote at y equals 0. Now, we know it approaches 0 from above as they get closer towards positive infinity and negative infinity, so I have this general shape. As I get close to negative 2 from the left, I know it goes towards positive infinity. Let's just check that. Negative 2, yep. And also this one goes towards positive infinity if it comes from the right. So we have a general shape so far like this. Okay. As I approach negative 2 from the right, goes towards negative infinity, and as x approaches 2 from the left, it also goes towards positive infinity, so that means your shape must be something like this. You can verify that it doesn't cross the x-axis at all because the numerator does never, ever would equal 0. And there you go. That's what your function f(x) should probably look like. So let's look at one that doesn't fit that same conformity. So in this case, to figure out the vertical asymptote of this function, f of x equals 2x squared over x squared plus 1, you cannot solve for x in the denominator. So this one has no vertical asymptotes. There is, however, a horizontal asymptote. So again, we're looking at the limit as x approaches plus or minus infinity of this function 2x squared over 1x squared plus 1. Well, that is just going to equal 2. So it's going to approach the value 2. Now again, we can separate it into both left-hand side and right-hand side. If you choose a very large number, let's say 1,000, and put it in, let's just see how it approaches. So after plugging it into my calculator, I noticed that both of them actually approach from below. Okay, so because we don't have vertical asymptote, we need some more information. So let's find out intervals of increase and decrease. So first of all, we've got to determine our derivative. So I'm going to rewrite it first, like this, as a product of two functions. Now I'm going to apply my derivative. So I find the derivative of the first one, which is 4x. Leave the second one alone. Leave the first one alone this time. And now I got to find the derivative of the second one, which requires chain rule. So x squared, I can bring the negative 1 down, it becomes x squared plus 1 to the exponent -2, and now I got to find the derivative of what's inside, which is 2x. From here, to better calculate when I have zeros, I should try to factor it. So you might notice that there's a 4x that's common between both of them, and there's an x squared plus 1 to the -2. We always choose the one with a lower exponent. That's common. So that leaves me with an x squared plus 1 from the first term. Leaves me with a, let's see, sorry, thinking here, -1 and an x squared from the last terms. So I simplify even further. Well, this set of square brackets actually turns out to just be equal to 1. So 1 times 4x is 4x all over x squared plus 1 squared. Now to find out my intervals of increase and decrease, I need to know when this is 0. Well, rational functions can only be 0 if the numerator is 0. So when is 4x equal to 0? Obviously when x equals 0. So now I can create an interval chart for this. I'm going to break up this function a little bit more than I usually have. So I'm going to look at x values less than 0 and x values greater than 0, because my function is both, my first derivative is a product of 4x divided by x squared plus 1 squared. I'm going to break them up like that. That's going to give me f prime of x. Therefore, I'll figure out what f of x is doing. So, if f of x is less than 0, this is going to be negative. This next function, I'll square it, plus 1, square it again, positive. That means overall the function will be negative. And that means our function's decreasing. Okay, so substitute the value greater than 0 in. That means this is going to be positive. This will also be positive, meaning this one's positive, and therefore the function's increasing. So now we try to see if the actual value x at 0 makes sense by substituting into our original function. Well, we substitute into our original function, we get 0, and that means the point 0, 0 is a local minimum. Excellent, we found actually another point. Okay, so to save us a little bit of time, I worked out the derivative of this, the second derivative here, and set it equal to 0, and solved. I found values of exactly plus or minus 1 over root 3, or approximately 0.6. You can verify this on your own if you'd like. So I'm going to fill out this chart here. For the interval chart, this is going to always be positive for the first row. The second row, it's a quadratic, opening downwards. So that means it's going to be negative, positive, and then negative. The third row, it's a squared value again, plus 1 cubed. So that's always going to be positive no matter what I choose. So that's going to give me a second derivative that's negative here, positive here, and negative here. So let me use some shapes here. I'm going to use this shape for concave down. Also, because I know it's going to be decreasing in this area, x being less than negative 0.6, I'm going to use that shape. Now, because in our previous problem, we know that it goes from decreasing then to increasing. And now it's going to be concave up between negative 0.6 to 0.6. I'm going to use this shape to represent my concave up. Or you could just state concave up, concave down, and so forth. And then this shape would be concave down again. So now you start to see the shape that it's going to actually take. So since these values of plus or minus 1 over root 3 did give us some information, we find the point right here. And therefore I could define the points. Therefore, plus or minus 1 over root 3 and a half are points of inflection. Again, points of inflection are points where a function changes from concave up to concave down or vice versa. Okay, so now what we can do is we can draw a sketch of what this graph might look like. So let's say this is where the value 2 is. So that's going to be our horizontal asymptote. Okay, I'll place the, let's say this is where 1 is, and where negative 1 is. That means 0.5 would be halfway between, and 0.6 is just slightly closer. So let's say this is where negative 0.6 is. And this is approximately where 0.6 is. Okay, so we know we have at points 0.6 and 0.5. We have another point of interest. And negative 0.6 and 0.5, we have another point of interest. And at point 0, 0, we have a point of interest. So I'll put those points first. You know, before negative 0.06, it was decreasing and concave down and getting closer to this asymptote. So we could have something like this kind of shape right here, concave down between negative 0.6 and 0. Oops, a little too close. We had something that was concave up from 0 to 0.6. We had something that was concave up and increasing, and then still increasing after 0.6, but now starting to get concave down. You get this kind of shape. And that must be what our function looks like. And thus concludes